Hello, class. I have had breakfast and got a coffee in the microwave that I'll probably have to grab before I start this lecture, but that's okay. Just going to start my timer. I'm going to go and grab that coffee. And there we go. You know, this lecture that I want to do now, you can see across the top of the lecture screen, I want to talk about the conceptual aspect of divergence. I want to talk to you about the two Gauss's laws that make up two of the four Maxwell's equations. And now, excuse me, I also want to talk about the magnetic field and the attractiveness and repulsiveness of the magnetic field and why that occurs and how we should look at it due to current flow. Not entirely with this course so much as it would probably, you know, I'm sure that you looked at this a lot when you were working with motors and controls, is magnetic field due to current flow and stuff like that. And I'm just going to talk about a couple, you know, minor conceptual things, because I would suppose that you guys have really understood all about magnetostatics and everything when you took motors and controls. Not sure who you took that from. I think it was Afsani who was teaching that, but I'm not sure. Anyway, so I'm not going to go so deep in that because you guys already have all of that. Now, let's talk about divergence, right? Now, divergence, let's say that I have a point in space. And my divergence coming out of there, my electric field coming out of there, right? If this is a positive thing, let's just put that down there. If that's a positive charge, and I would see that in all directions, let's put a little circle around that. It really wouldn't be a circle so much as it would be a sphere, wouldn't it? I'll just draw a sphere like that. And then if this was a proton, if it was a positive, then it would have, right, flux lines coming out in all direction of that sphere, right? And we've worked with Gauss's law before to actually figure out how much would be coming out of there. And as a matter of fact, I thought that I would do another just quick example here. You know, when we think of divergence and we think of Gauss's equation, right? That the flux through the sphere has got to be equal to the charge contained in the sphere. But what if we're only looking at a certain part of the sphere? Would only, let's say, 1/16 of this come through 1/16 of the sphere, or would half of it come through 1/16 and all the rest goes someplace else? I think everybody can see that this is isotropic. And if you don't know what isotropic is, it basically is stating that things happen in all directions, omnidirectional, right? It's totally uniform. And that's what this is. It's totally uniform. And so also, it looks at the divergence of that, right? So when we're looking at the divergence of D, or you can call it, you know, epsilon E, whatever, divergence of D, divergence of E, what are we really looking at? This is what we're looking at. We're looking at if I was to form a sphere in 3 dimensions, or if in 2 dimensions. Why is that off there? Oh my God, what's going on now? You know, the autofocus should be working. Let me fix this up. I will be, well, I'll tell you, there's one way that I can sort of fix it a little quicker. There you go. You can look at me for a second. Ah! I actually pretty, you know, as far as the resolution of the screen goes, it doesn't look too bad. And then this should snap it back into focus, but it hasn't. I'm going to stop and just manually focus the camera. I'll be right back. Well, I tried to change it, and then I couldn't, and then I came back to it, and it changed itself and it corrected itself. So that looks a lot better. I'm sure that's still on manual. Sometimes it just does weird things. I know, but that's what I expect from LIT, because LIT is about the most incompetent group on the campus that I know of. So, you know, we could have had literally a kindergarten person help us through this pandemic, and they would have done a better job. All right, let's get back to this. So that's one side of Gauss's equation, is the divergence of the flux. And so isn't that what we have? Now, when this comes out like this, that would be a positive divergence, right? I'm going to draw another one. Let's say that instead of having a proton there, I had an electron, so that this was a minus charge. And I think everybody can see then that the isotropic electric fields and the flux lines would all be going in rather than out, right? And if they're going in rather than out, then they are negative divergence, right? Now, I want to point out something too. It really depends on where I draw that circle, doesn't it? Right here, we can see that it's they're all going in, and in is negative for divergence, and out is positive for divergence, right? So this would be an electron. Let me just say something like an electron, and this would be something like a proton over there. They're point charges, and one is pushing that field out because it's a positive charge. The other one has the field lines coming in because it's a negative charge, and that's what it is. So this over here equals a positive, and del dot D over here equals a negative, right? So I just wanted to point that out to you. But what about if instead of taking it at either one of those, let's just say that we have, I'll just look at it in 2 dimensions now. Let's say we've got the proton here, still that plus charge, right? And now in 2 dimensions, this thing is, you know, fluxing in all directions isotropically, so it's uniform. And so it is going out in all directions. Now, let me extend this just a little bit out here. Let's say that we, you know, I'm just extending these lines so that we can sort of see these lines a little better, right? Now, let's say instead of me taking the circle right here, right here, that would be a positive divergence, because you can see that everything's going out, right? So it's a positive divergence. Over here, this is a positive divergence too, but what if instead of taking it around the point charge, I was to take it out here? Now, there's no point charge out here, is there? No, there's not. I got all the lights and everything on, so we should have enough light here. But out here, what do I really have? I have things coming in here in this side, right? I have things going out the other side. So remember what Gauss's law says, and you know, I'm talking about this in 2 dimensions, but I'm really talking about a 3-dimensional sphere that I've put out here. Now, there's no charge inside that sphere, right? That sphere has no charge inside it. So when I look at that sphere, because what is it? What does Gauss's law says? Gauss's law says that the flux out of a sphere that I put around that area, just like I put a sphere around this area, and I'm looking at the flux that's coming out of it, right? Basically what I'm doing is I'm counting all the flux lines coming out and I'm subtracting all the flux lines going in. And as you can see right here, there are no flux lines going in, are there? There's just flux lines coming out. Very similar to the derivation I made with Gauss's law originally, right? So that's going to be a positive number, positive integer, right? And this one here is going to be negative because do I have any lines coming out? No. Negative lines are, lines going in are negative, lines coming out are positive. I got no lines coming out of there. How about this one here? Well, we have lines coming out, coming into it, right? There's lines coming into it. Do we have any charge inside that sphere? No. There's no charge inside that sphere. There's a charge inside this sphere. There's a charge inside this sphere. There's no charge inside that sphere. So what does Gauss's law tell us? Gauss's law tells us that the flux out, the net flux, let's just write that. The net flux equals 0. Now, does the net flux equal 0 here? No, it's a negative number. Does the net flux equal 0 here? No, it's a positive number. But over here, we've got the same amount of lines coming in, right, as we have going out. So over here, when we're looking at that, I'm going to write this in is del dot D equals 0. I want to emphasize that if there is no charge in here, so the net flux, once I subtract all the lines going out from all the lines going in, that gives me 0, right? There's no charge inside there. And that follows Gauss's law too, because Gauss's law says that the net flux that's coming out of there has got to be equal to the charge inside, and there's no charge inside that sphere. There's charge inside this sphere, there's charge inside this sphere, but there's none in here. So I know that the divergence of E or the divergence of D has got to be 0 for this sphere, because it's not surrounding the charge in any way. It's just out here, has lines going through it, not surrounding the charge. So the net flux is going to be equal to 0. I'm not going to keep going, on with divergence. There are so many good videos and stuff out there that you can look at that will explain divergence and Maxwell's equations and everything else. But I mean, that's what I'm here to teach. So we'll do this. Now, the next thing that I want to talk about is Gauss's law of magnetism, right? So everything up here is all Gauss's law. So this is really all my divergence. But what is Gauss's law of magnetism? Gauss's law of magnetism. Gauss's law of magnetism said that if I were to take the divergence of the magnetic field flux density for anything, that equals 0. Just like my flux, I'm out here, the amount of flux coming in equals the amount of flux going out. That means that the net flux, the divergence of the flux, is 0. There's nothing coming in, there's nothing coming out. Here, got a lot coming in, going out. This would be negative, that'd be positive. But this is Gauss's law of magnetism. And basically what Gauss's law of magnetism is saying is that we don't have separate charges in magnetism like we do in electricity. In electricity, I can say this is a proton and this is an electron. You know, I have methods by which I can separate a proton from an electron, right? I can strip electrons away. I could even make a stream of electrons if I wanted to. Totally separate particles. How about the North Pole of a magnet? If I wanted to separate the North Pole of a magnet from the South Pole of a magnet, well, I just couldn't do it. I just couldn't do it. Let's just draw a magnet here for a second. And I also want to draw, that's my North Pole and that's my South Pole. I also want to draw some flux lines, right, coming out of this magnet. Let me just draw a couple flux lines here. Now we have direction with these lines too, as you know from your motors and controls course, is that whenever we draw magnetic field lines, we have to actually draw the direction. It is a vector after all. So here are my magnetic field lines as I'm drawing them. And of course, you all notice that they emanate from the North Pole and they go to the South Pole, right? and you're all saying, well, I don't understand, Professor Grinquist, because you tell us that, you know, there's no magnetic monopoles, and but I can draw a line, I can draw a sphere, a circle, where we only have lines coming out, right? And so people say to me, okay, well, I'm going to draw a sphere right here. And then I've got lines, you know, coming out of that sphere. And I say, no, you don't. You don't have any lines coming out of that sphere. You don't have a net, right? You haven't invented monopoles. If we haven't been able to do it, you as a student probably haven't been able to do it either. And where are you missing? Now, if you look up here, that's what happens when you talk all morning. You see why I bring a coffee to our morning meetings sometimes? You have to have something to drink if you're talking forever. So now let's look at that. You're probably saying to me, hey, you're wrong, because the sphere up there that you made, you've got lines coming out of it, but there's no lines going into it. And of course, that is not true, is it? That's not true, because there are lines going into it, aren't there? Inside that magnet, there's a magnetic field. So inside that magnet, we're going to have lines going this way, aren't we? Right? So if I was to blow up that end of the magnet, let's just look at that right here. Just going to blow up that end of the magnet, my North Pole end. And if we do that, we basically see that my magnetic flux lines are coming up through here, right? Coming around and then going back down through here, right? So we've got it coming in. If I was to draw that sphere at the top end again, right? There's my sphere that I'm putting up there to find out how many lines are going in and how many lines are coming out. Well, I have the same amount of lines that are coming into my magnetic field, right, as I've got going out of my magnetic field. Right? So that's why it's zero. And in fact, all what we're really saying with Maxwell's second law is there are no monopoles. no monopoles. And you're probably thinking, well, I don't know. I'm just going to keep splitting that magnet in half until I get a monopole. Well, good idea, but you'll be way down past the atomic level when you realize that it can't go any further, and you still haven't gotten a monopole. And that's right, there are no monopoles, magnetic monopoles. There are electric monopoles, and we call those positive and negative charges, right? And is it that we may not have just gotten to the point, maybe in the future we will find a magnetic monopole? And in fact, if we find a magnetic monopole, we'll be flying all over the universe in relatively quick time period. We'll see how it goes. You know, my whole life has just been a series of things that I have imagined, and then those things have existed in reality. And I think I told you about the concept when I was a child. I was with my mother in the priest's rectory, and he had a dictaphone. And I asked my mom, what does that dictaphone do? I mean, I was probably 7, 8 years old, right? What does this thing do, Mom? And it looked like a typewriter with a microphone attached to it. I mean, an old typewriter, because let's face it, I'm going back to the Stone Age when I say I was 7 years old. So my mother said to me, oh, that's a dictaphone. What the priest does is he talks into that and then it types. I said, types it by itself? He said, yep, he talks into it, and you know, that's all he has to do. He just talks into it and then types it by itself. Now my mom wasn't really explaining it correctly to me, and I walked away, you know, being in 2nd or 3rd grade, thinking, oh my God, they've got a machine that you can talk into, and it writes all of the stuff out that you're talking into it. So I eventually mentioned this to my dad and explained how my mother had explained it to me. And my dad said, no, that's not right, Scott. That's not right. It's a microphone that goes to a recording device. And then the parish secretary, right? The parish secretary, a human computer, types it out for him off that. And I thought, I was so disappointed. And I said to my dad, well, you know, do you think they'll ever have one of those, Dad? Now, this is in the 60s. I know, to even say 60, it makes me just think I'm so old. But my dad says, no, my God, in our life, Scott, they're never going to have any type of device whatsoever where you could talk into it and it's just going to write it out for you. That's just science fiction, right? I mean, it was 1966, I think, right? So 65, 66. And I thought, okay, well, I can see that, because how could you ever make a machine like that? And here we are today, 20 years past Drag and Dictate coming out, right? I use Drag and Dictate. I use Drag and Dictate #1. I use Drag and Dictate all the time, right? I never type in a text message into my phone. I never would do that. Everything I do, writing emails, they're all dictated, mainly. And that's the thing. You've got to constantly improve your productivity so that you can do other things that you might want to. And that's what I'm doing here. And I hope everybody understands all of this. And I hope you understand the second Maxwell's equation. You know, another thing that I want you to learn here is that these are not Maxwell's equations. These are equations, a set of equations that Maxwell put together that were connected symbiotically prior to that, but, you know, no one had just sort of put them together. So they call them James Clerk Maxwell's. I'm sure Gauss is rolling over in his grave thinking, I donated 2. I donated 2 of the 4, and James Clerk Maxwell only donated 1/2 of 1 of the 4 equations. He gets his name put on there. I get nothing. But the truth is that that's not true. I mean, Gauss got a lot of things and is well renowned. Now, I want to do just a short example. I was going to do this, and this will help you too. Let's say that we want to use Gauss's equation, but we don't want to do it for the whole sphere. let's say we only want theta to between 0 and 90 degrees. Now, usually theta in a spherical coordinate system, right? Spherical coordinate system. We're using that again, and I hope people more and more are feeling more and more comfortable with integrating and everything in a spherical coordinate system. We'll look at some things when we get to coax cables where we use the cylindrical coordinate system too. Anyway, let's do an integration in the with Gauss's law. And this phi, which goes from 0 to 2 pi usually, is only going to go from 0 to 45 degrees. All right, so I'm limiting those two things. We've got a point charge inside. I'm going to say that our point charge inside is just going to be Q. I actually have a good example along with this problem, but you know, so we could get stuff more in depth. I'm not going to go into that right now. I just want to show you the integration and how you would be integrating Ohm's law in the integral case. So, what is the flux? I didn't say flux density. I said, what is the flux just through this surface? Now, I want to draw a sphere for a second. Right? There's a sphere. Now, I'm going to go from 0 to 90. In fact, why don't I draw the sphere like this? Right, there's my equator right there. So I'm getting a two-dimensional thing of the sphere. Right? Now, 0 to 90 with theta. Well, 0 to 90 with theta would mean that I would have all of the northern hemisphere, right? 0 to 90 is all of the northern hemisphere with theta. How about phi? Now, phi goes from 0 to 2 pi, doesn't it? So if it goes from 0, let's say that that the top of this here is 0 degrees, and he's going 45 degrees. Now, how many do I have to go? I'm only looking at half of this right now, right? So I would only have 180 degrees on this side. So that would be 1/4 of the sphere. So if that's 1/2, then this would be 1/4, wouldn't it? If you looked at that, or I suppose I could done it in here, it'd be like, well, actually it would be it'd be 1/4. I shouldn't say that. Is that 1/4? No, it'd be 1/8. 1/8. I had that right. 1/8 of that. Or actually 1/16, because 45 goes in there 8 times. So 1/8 of the normal. Anyway, we should have one. Okay, so the surface area equals the total surface area 4 pi r squared. That's the total surface area of a sphere divided by 16. And I would expect that the flux is also going to be 1/16 of the charge. There, that's better. So let's see if that is the case. So if the flux is just going to be for a point charge is Q over 4 pi, and then well, should I bring, if I I don't want to go through that all over again, but if I drew a sphere, right, spherical coordinate systems, I would see that that if I had a little thing here, I'm going to refer you back to the thing, and I was just looking at that small cross-sectional area, and then I'm just going to integrate to get that small thing. But what is that? What is that window? Wasn't when I talked about it before, just the square, just that little square on the surface of the sphere. What is that differential surface area called? And I think everybody can remember back that it is r squared times the sine of phi times d phi d theta times d phi. So sine of theta, d theta, d phi, r squared starts it off. And we did that before, and then I'm just going to do that too, except let's look at our integration now. 0 to pi over 4, right? That's the 45 degrees. And the 45 degrees for phi. And then here's my other one, 0 to pi over 2, right? That's the 90 degrees for d phi. And then that would be times sine theta, d theta, d phi. All right. Well, let's do that first integration first from pi over 4 to that of sine theta. And isn't that minus 1? So let's do the flux. We've still got the q over 4 pi out in the front. I think everybody can see that the r squared that was in the denominator there is now canceled out with the r squared that was originally there, right? Let's take that r squared there. Some people might say, hey, where you left out r squared? No, I didn't, because I had r squared in the denominator here, and that canceled out with the r squared that's there. That's where we got rid of the r squared. Okay, so I sort of did 2 steps all at once because there's a lot of writing to do. I think everybody can see that. So now let's go back to this. So if I've got sine theta d theta, the integral of that is minus cosine. So let's put that up there. So minus cosine, and I want to evaluate that minus cosine between pi over 4 and 0, right? I still have the integral from 0 to pi over 2 for d phi, and I'll do that in just a second. Now, pi over 4 is 90 degrees. Oh, wait. Pi. Oh, that's not pi over 4. That's pi over 2. What am I doing? Where is that thing? Oh, no, I've lost it. Oh, no, here it is. That's right. I'm doing the not the 90 degree. I'm doing the 45 degree. Oh wait. Yeah. It should be 4 d phi. Yep. And this should be 2. See, in the morning, I catch my mistakes if I make them all that much quicker. That should be 2. All right. And I knew that. So the cosine of 90 degrees is 0, right? Let's put a minus in front of that 0. How about minus 0? So I've got q over 4 pi times 0, and then what's the cosine of 0? Well, that's 1. Minus a minus 1, right? Everyone see there's 2 minuses there? So 0 minus a minus 1 gives me 1. And then I've still got my integral here, and since I'm just integrating over phi and I've got pi over 4 to 0, I have pi over 4, right? Because the integral of d phi is just phi, and I'm evaluating that from pi over 4 minus 0. So pi over 4 minus 0 is just pi over 4. I think everyone can see that the pi's cancel out, and so we get the flux is going to be equal to the charge contained inside divided by 4 times 4, or 16. And of course, that's what we expected, isn't it? Right? Because the area, the surface area that we're looking at is only 1/16 of the surface area of the sphere. So we would expect that fluxing through there would be 1/16 of the flux, right? Okay, well, I'm going to hold it there. We're going to start to get into a newer field. You know, I haven't really discussed del dot B equals 0. I'll talk about that and Gauss's law, because we've sort of finished those two laws now. So we're half done with the amount of equations in Maxwell's equations, but we still have the lion's share of the course to still do. The heavy lifting of the course is still in front of us, and the heavy lifting for James Clerk Maxwell equations are still in front of us too. Okay.